Hello everyone, and welcome to this new episode of CONSELF webinar series. My name is Alessandro, and today I will show you a new feature of CONSELF Simulation Platform 2.4. First of all, a few words about CONSELF. As you can see from this slide, we are an Italian-based company, but we are present worldwide with our distribution network. And today is the first date of our 3 webinars that will be in the next week and in the one after that on the 21st and the 28th of July, dealing with multi-phase and buildings to complete this series. As you can see here, our references are available for you to connect, to follow all our updates, and also to contact us with the mailing address. A summary of our activities. The first and the most important one is the simulation platform on the cloud that allows you to perform fluid dynamics and structural analysis in a common browser. The complete cycle from geometry upload to result post-processing can be performed directly online. We also provide a cloud computing service where you have the modern high-performance hardware on demand, paying just for the time you actually use it. And finally, we also have an engineering consulting service to provide optimized design and simulation technology. What we are gonna see today is basically a very cool new feature of CONSELF simulation platform, and we will see how to import a geometry from OnShape. OnShape is a fully cloud CAD. It's a very innovative approach to the modeling, and you will see how this works. Then we will, after the import, we will set up an external flow CFD simulation. And finally, we will take a look at the pressure and velocity plots, as well as the flow streamlines. So let's shift from the presentation to the browser, and let's take a look at what the whole simulation cycle will look like. So, as you can see here, we are our CONSELF homepage. Under the menu Services, Simulation on the Cloud, you have a description of the simulation platform. And we will see that it works in a step-by-step approach. The very first thing to do is to log in and register and sign up for the welcome plan. It's 100% free and allows you to try the platform, giving you 20 simulation credits per month, every month for free. In order to sign up for the plan, you have to go under Store and Products, Cloud Simulation Plans, and here sign up for the welcome plan. Once you complete the checkout without any need of payment data, you can log in into the platform by clicking on the top right under the login button. As you can see here, you have to insert your credential, and then you will be inside the application. The very first tab is the dashboard and presents you few information about your account with the credits remaining and spent, credits spent for the last simulations, and all the steps you run. Under the Storage tab, you have a list of all your previous cases. You can delete them. You have an information about the disk you're using with your cases, and also a split for the disk amount occupied by every single case. In order to start a new simulation, you have to go under the Simulations tab, and here you can create a new case, select an old one, or monitor your case in progress. So today we are going to use a geometry that is on OnShape. Let's first name our case. I will call it plane, because as you will see, we will be dealing with the new concept of an airplane. So clicking Create, we are in the very first phase of our simulation, the step geometry. And now you can upload a CAD model from your own PC, or as you can see here, import it from OnShape. So let's take a look at OnShape. As you can see, it's a Cloud CAD with the common way to interact with your model. You can shape it, you can create surfaces, volumes, and so on. And once your model and your document is ready, you can save it, and then you can go to CONSELF and click on OnShape Import. Then here you will have the menu with all your OnShape documents. And in our case, we are going to take the ortho plane. You have a preview here. And so you click on Import Geometry, and the CAD model will be loaded inside CONSELF. The process is quite fast. It depends on the dimension of the CAD, but as you will see here, we will have our geometry showed in the graphical window. So my model is in inches, and so I will select in the first parameter here, inches has a 5 units dimension. Clicking Next, we are in the second section of the geometry, and we have to choose between external or internal flow type. We will analyze the external aerodynamics of our plane, and so the air flowing inside our virtual wind tunnel and interacting with our surface. So it is an external flow, and choosing it, you will be facing 6 different parameters of the so-called bounding box. Here you will have delta x minus and x plus, and same thing for the other 2 dimensions. And basically here you have to prescribe the dimension of your virtual wind tunnel, of your domain. So basically, where are you going to put your plane inside a virtual wind tunnel, and here you have to assign the virtual wind tunnel dimension. They are given by delta and in terms of file units. So it means that if you take a look at your sizes, and you can do it by clicking on the small I, you see you have 1,400 in X, 118 in Y, and about 600 in Z. So it's a good choice to leave enough space between our model and the boundaries so that the CFD simulation will run smooth and without any problems. And so in order to do so, we assign 1,400 on X, 300 on Y, and 1,800 on Z. The same thing for the plus. And I'm doing it because we will simulate the flow entering from Z minus directed toward the z-axis, so this way. So I'm going to leave 1,400 inches on the right and the left of our plane. It means that I'm leaving the same amount of inches that is occupied by the plane itself in the x direction. And the y, so top and bottom, I'm leaving almost 2 times the sides, and in the z direction, I'm leaving about 3 times it. This is because the main interaction between the fluid and the surface will be directed along the z-axis. So this is a good choice for our bounding box. And now, in order to complete the geometry phase, we have to assign a group to these boundaries. As you can see, my plane is composed by many surfaces. All these surfaces will behave the same way with respect to the fluid. In particular, they are going to apply friction to the air, so they will impede airflow, deviating the flow, and they will act as a wall. Technical term is a no-slip wall. So I can group the entire surfaces together, and I can do that by selecting here under the selection menu, select all. As you can see, I have the whole plane selected, and then I click create boundary, and I name it wall. I can rename the boundary or edit it here in the manage boundary. As you can see, by double clicking here, you can rename it, you can even delete it. Okay, so now in order to do the same thing, okay, you can select all and create a boundary. Let's call it plane. Okay, now we are ready. We can submit. This step is completed, and we can hit on the submit button. And as you will see after confirming, the case will be in the case in progress menu. And so, as it will be completed, you will see your case under the selection of cases menu. And we can open it and continue our simulation. The geometry step is a very quick one. It is needed in order to prepare your geometry and your bounding box for the rest of the simulation. So we can wait until the process has been completed. It will be a few seconds. Okay, we are ready. We can open it, and as you can see there, now we are in the second step, the Mesh 2D. The very first thing to do from now on for every step is to choose from which step we want to start from. In our case, we just run geometry. We have to select geometry, and you will see here we have our bounding box with the plane inside. So it's in mid-air with the distances from the boundaries as prescribed during the geometry step. From now on, we have to deal with mesh generation. And the first thing to do is the surface mesh generation. In order to do so, we have to select each boundary we have. There are the 6 boundaries for the bounding box and 1 for the plane. And for each of them, we have to prescribe two parameters, the uniformity level and the max element size. Max element size is a characteristic dimension that is linked with the dimension of triangles that will discretize our surfaces. For the plane, we can choose 0.25, and be careful, from now on, you will be using always international system unit of measure. So the plane, we can have triangles with a characteristic dimension around 25 centimeters. For all other boundaries, we can use 2 meters, that can be good enough for our case. You have to select to add this value for every boundary. And then you will be ready to run the Mesh 2D step. The uniformity level is a parameter that prescribes the speed, or let's say how smoothly boundaries elements changes from a very small dimension to the very high one. Let's say you have two different boundaries that are neighbors, and on one you have very small elements, on the other one you have big elements. If you assign a high value or a uniformity level, the transition will be very smooth. As 70% is a good default choice. So we are good to go. We can click submit. I'm not going to do that because this process is like few minutes long, and so I already have the output of this process, and I'm going to show you the results of this operation. So I will open the plane. This is my case, and so we just completed Mesh 2D, and we will be in the Mesh 3D section. Again, the first thing to do is to select the step from where to start from. This is the Mesh 2D. In case you run multiple Mesh 2Ds, on this select, you will have more than one item from where to choose from. So let's choose the Mesh 2D and just take a look. Now we have our bounding box divided into small triangles. These triangles are around 2 meters wide, as prescribed, while the plane inside, as you will see, has very smaller triangles, around 25 centimeters. So, okay, this is the Mesh 2D result. And now we have to create the volume mesh. In fact, we are in Mesh 3D. We have to choose between two different algorithms. One is ixohedral and the other one is tetrahedral with boundary layer. For this case, I'm choosing the tetrahedral one. Then we have to prescribe the max element inside our domain. We used 2 meters for the bounding box. We can assign 8 meters for cells inside the domain. And we can go to the next step by clicking next. We are in the boundary treatment section. Boundary treatment behaves differently in case you are in the ixohedral or tetrahedral meshing algorithm. In order to find out what's the difference, you can take a look at the user manual by clicking on the bottom left button, and here you have a step-by-step description with all parameters you have to assign of our cloud simulation platform. As you can see here, in case of the tetrahedral boundary layer, you have the boundary treatment that will create a very small cells near the surfaces. This is called the boundary layer mesh. So the two parameters we are going to set are the layer number, so the number of layers near the surface we want to create, and the dimension of the first cell. So let's go back to the platform, and we want to add a boundary layer mesh on the plane. So in order to do it, we have to select the plane boundary and change layers number to 5, for example. And remember, we used a triangle characteristic dimension of 0.25. So I'm going to use a 0.01 for the dimension of the cell near the surface. So as you can see here, this dimension will be really small if compared to the triangle dimension. So now every other boundary is 0, so that the boundary layer is deactivated on those boundaries, and we can submit to obtain our volume mesh. Let's take a look at how at the results of this step in the CFD step. So again, first thing to do is to select from which step we want to start, in our case the Mesh 3D, and a new graphical window will appear. In this graphical window you have more items to deal with, filters that can be applied on your solution. For example, we can take a look at the inside of our mesh. We can just click on the solution file, click on the plus button, the clip. Once you select the orientation, the representation can be surfaced with edges in order to highlight the cells inside. As you can see, we have the entire volume with tetrahedral elements, and very near to the surface we have a boundary layer mesh, very regular, with small cells near the wall. Okay, so as you can see, the first cell is very small, and this is needed when dealing with very high velocity flows in order to catch the near wall behavior. Another interesting feature is the mesh quality parameter. Highlighting the first solution, the mesh file, you can color it by mesh quality. Coloring by mesh quality will highlight poor quality mesh zones. When taking a look at the legend, you see here mesh quality is in range between 0 and 0 basically. So the mesh is good and there are no problems. Okay. In case you will have a mesh quality between 0 and 1, it would mean that you have cells with a mesh quality value equal to 1, that these cells are poor quality mesh cells. So you can highlight them because the color would be red, and you can spot them in your domain and proceed to improve mesh refinement in the vicinity of them. Our mesh is good, so we can proceed with the simulation now. And this is the CFD part. So the first thing to do, as you can see, we will be dealing with 3 different sections. The first one, you have to prescribe the fluid model and the turbulence. At the velocity we are going to use, even if it is air, we can treat the fluid as an incompressible one. Turbulence model, we can choose the Spartan mouse. Then you have to assign fluid properties, air, so this is the density, and then we have dynamic viscosity. Finally, we have to prescribe the fluid and turbulence initialization. For the fluid, we can have 1 atmosphere, and the fluid will be at rest. As an initialization value for the turbulence, we can use the dynamic viscosity. Then we can proceed and go to the boundary condition. So first, let's start with the plane. As we were saying at the very beginning, the plane is a surface, as a wall, that will apply friction to the air, so velocity on the plane will be 0. This is the so-called wall no-slip condition. Then, for x minus, y minus, x maximum, and y maximum boundaries, since they are aligned with the flow, we can prescribe the symmetry condition. They are far enough with respect to the body that we can suppose they will behave as symmetry boundaries. Okay, and finally, Z minus and Z maximum. Okay, well, the flow enters from the Z minus, and in this case, we have to apply an inlet because the flow enters from there, and we will assign the velocity. In this case, we use 100 meters per second, and here you have to prescribe the hydraulic diameter, that in this case can be used around 25. It's a length and is linked with the dimension of your inlet boundaries. Finally, Z max is the outlet, and you have only one choice, is the pressure outlet, where you assign 1 atmosphere. So the flow exits in a room, let's say, where it encounters 1 atmosphere of pressure. Okay, good with the boundaries, and now let's move to the simulation settings. You can choose a steady analysis or a transient one. We can perform a steady. For this case, number of iterations can be set to 2000 and save a solution every 500 iterations. So CFD is ready to be launched, and let's click. If we click submit, the process will restart. And we will again skip this in order to avoid waiting a few minutes. And let's go back straight to the result. So as before, here we had to select again the step from where we want to start from is the last CFD. And we can post-process our results here directly online, or we can download them on our own PC to post-process them locally. First thing to do is to take a look at the residuals. As you can see here, after first oscillating behavior, we have a very smooth trend that indicates that the residuals are dropping, and this is a clear sign of a good simulation result. Okay, so now clicking on the small clock, we can go to the last iteration, and we can start to take a look at the variables inside our domain. Again, we will have apply a few filters in order to take a look inside. And the first one is again the clip. Now, as you can see, the clip is called by different variables. In this case, the pressure. And taking a look with a small zoom, you see, as expected, the flow enters from our left, encounters the airplane, and the flow is deviated toward the upper and the lower part. So the peak of the pressure is in the nose, and as you will see here, there is a zone with a very small pressure. This is the reason why wings generate lift, and this is the behavior of the flow. So high pressure on the nose, small pressure on sides, on the upper and lower side. We can also take a look at the velocity, and obviously it's very small near the nose where the flow hits our plane, and then it is accelerated towards the upper and lower part of our body, reaching the maximum values. Let's say we want to take a look at the flow field, and in particular the trajectories of our fluid particles. We can do it with the string tracer. String tracer, as you start to understand, shows the trajectories of our fluid particles in our domain. So here I'm just setting my point source, so where I want to initialize my particles, and then you can see here, you can also color them. Here they are colored by pressure. In fact, they are red in the zone of the nozzle, the nozzle, and they are blue on the top and bottom part. You can also color them by velocity, and again, as expected, the highest peak value is on the upper part of our wing. So this was a very simple example of what you can do with our cloud simulation platform. And as you saw, we performed the entire cycle inside a common web browser. I'm using Google Chrome, for example. You can use every major internet browser like Mozilla, like Safari, like Internet Explorer, and obviously from every operating system like Windows, Linux, or Mac. Let me just switch back to the presentation. So here you can see how you can ask questions. Just follow the instruction and I will be answering them live. In the meantime, I just want to remind you that there is a 100% free plan available on our website. The welcome plan gives you 20 simulation credits per month for free in order to evaluate the platform, to check the features, and try it with your models, with your CAD models. Our pay plans starts from 180 euros per month, and they include support, they include dedicated support, they include full access to all the application. We have dedicated application for a lot of different sectors, and you can access the entire set of dedicated application with a single subscription. Remember, it is all online. You don't need any particular hardware to run simulation on our servers. You can even access it from tablet and interact with your simulation, check out results, and also you can also send your simulation, turn off your PC, check if the simulation is complete or not with your tablet, and then come back later. So it's a very flexible tool that allows you to take advantage of the state-of-the-art technology. We are based on OpenFOAM for the CFD part. OpenFOAM is a very well-known CFD library. It's widely documented, and the accuracy is comparable to those of the major commercial softwares. So you are sure of the quality of your results, the results you get from CONSELF. All this information can be found on our website under the dedicated page. If you need any additional information, write us at info@conself.com. You can follow our updates on our web page, but also on social, in particular on LinkedIn, on our page. Let's follow us. It's a very, very interesting place where we post also technical articles and news about the software. So I think we are okay now. Thank you all for watching, and remember, next week and the one before and the one after that, we will have 2 additional webinars on multi-phase application and buildings simulation. So just register on our website and book your seats. Thank you very much. Have a great day.